Okay, can you see the slide?
Yes.
Great. Okay, welcome to our second day's tutorial session. I hope you've all enjoyed learning the potential model yesterday. Today we will learn about another model in the deep potential family. The name is deep dipole. It's introduced to the DeepMD kit 2 years ago and has been used in many study of the electric properties of material. First, let's see what is deep dipole. Or it's called deep Wannier in other places. From first principle electronic methods like density functional theory, we can extract several crucial physical quantities. The most important of all is, of course, potential energy surface and the human Feynman forces. The deep potential model you learned yesterday is an effective representation of the potential energy surface. Then, in addition to the potential energy surface, the first principle, please mute yourself if you have no questions. The deep potential model you learned yesterday is it represents the potential energy surface, right? Then, in addition to the potential energy surface, the density functional theory also provide information on atomic or molecular electric dipoles. The electric dipole attached to a molecule mostly depend on its local chemical environment. So it's possible to find a mapping from local atomic coordinates to a dipole as a 3D vector attached to the central atom. The deep dipole model is exactly the tool for this job. The structure of a deep dipole model is similar to the deep potential model. From a black box point of view, it reads the atomic coordinates and returns you the dipole vector associated to each molecule. A crucial point here is that deep dipole preserves the rotational and permutation symmetry. So if you rotate an isolated molecule, the deep dipole model will rotate the predicted dipole vector simultaneously without changing its magnitude. Now, I hope you all get the basic understanding on what is deep dipole. If you are interested in knowing more, you can check the two references listed here. Then let's move to the exact definition of electric dipole and the training data for the deep dipole model. The electric dipole we are talking about are defined on electronic Wannier centers, like what Chunyi has briefly introduced in today morning's lecture session. For those people who are not familiar with the theory of Wannier functions, let's say it's just the geometric center of the localized electronic orbitals. I will be quite hand-waving in the following because I don't want to go too deep into the theory. Let's take the water molecule as the example. Each water molecule has 8 localized valence electrons living on 4 sp3-like orbitals. These 4 orbitals are quantum states with certain spatial probability distribution. The geometric center of the probability distribution is almost the Wannier center. Although the formal description of Wannier center is more complicated than my hand-waving explanation, the idea is the same. Now let's consider each Wannier center is associated to an orbital containing 2 electrons. The effective charge of each Wannier center is minus 2 elementary charge, right? We can take the geometric center of the 4 Wannier centers and call it the Wannier centroid. It's the purple circle plotted here. For water molecule, for water molecule, the effective charge of the Wannier centroid is then -8 charges. This Wannier centroid is equivalent to the negative point charge in a classical picture of electric dipole. Meanwhile, the oxygen atom and the two hydrogen atoms carry positive charges. Each hydrogen carries 1 and the oxygen carries 6 after canceling with the two core electrons. I can hear the noise. Okay, it stops. The geometric center of the 8 positive charges coming from the atom core is equivalent to the positive point charge in the classical picture of electric dipole. Then the molecular dipole for this water molecule is then defined in the classical way as the position vector pointing from the negative charge center to the positive charge center. The molecular dipole defined this way is used as the training labels for the deep dipole model. And the deep dipole model is thus called the deep Wannier model sometimes. I hope now you've all had the intuitive picture of how the molecular dipole is defined. However, there's still one more issue to consider if you are going to generate the dipole label from scratch. For those who are familiar with the theory of Wannier functions, you may already realize the issue is about non-uniqueness of the Wannier centers. In the general sense, the Wannier center is not unique due to gauge symmetry, so there is some complication on generating the training label from density functional theory. After clarifying this extra complication, we will enter our first hands-on exercise on generating a training data for the deep dipole. The extra step is called maximal localization of the Wannier functions. It's a procedure to get a unique set of Wannier centers that are closest to the localized atomic orbitals. The procedure is defined as an optimization problem on the second moment of the Wannier functions. I'm not going to explain the algebra here, but if you are interested in knowing more, you can check the review paper written by Nicola Mazzari. As a matter of fact, this procedure has been standardized and implemented in the open source code Wannier 90. The Wannier 90 code interfaces with most of the mainstream density functional theory codes like Quantum Espresso or VASP, so you can do such calculation quite easily. By feeding Wannier 90 the DFT orbitals, it can compute the corresponding maximally localized Wannier functions and the Wannier center. I highlight the mathematical definition of each Wannier center here. Then next, we are going to do a little exercise with Quantum Espresso and Wannier 90 to get the Wannier centers of a water molecule system. So to do the exercise, you need to follow the commands in the run.sh file in this folder on the virtual machine. It consists of 5 steps. So the first step is the basic self-consistent DFT calculation, like the ones you've done yesterday in Zach's session. Then we need to do a non-self-consistent calculation to refine the electron orbitals. The input to the SCF calculation and the NSCF calculation are basically the same, except for one line difference. You can check the input script by yourself to confirm that there's basically no difference. The next step is generating the input file for further post-processing with the Wannier 90.x code. You will feed the generated input to the, how do I get the pointers? Okay, cool. you will generate the input file for post-processing with this code. Then you will feed the generated input to the pw2wannier90.x code. It will automatically generate all the information needed for maximally localized Wannier function calculation. Finally, the Wannier90 code can work on the optimization and deliver the coordinates of the Wannier centers to you. After finish, you can download the atomic configuration and visualize the Wannier centers with Orbital. These 5 steps looks complicated, but it only requires a very small amount of work to build the input scripts. Specifically, the input of the Wannier90 code needs extra attention. Let's take a look. The headers of the input to Wannier90 is shown here. Most of the things are self-evident, except for the guiding centers. At the beginning, we only have you need to specify the number of Wannier centers. That's just the number of occupied orbitals. And that's number of electrons divided by 2. Then the number of iterations, the default value is fine. You don't need to change it. And this option is for outputting the coordinates of the Wannier centers and the original molecular system. So yeah, the only thing that may need a little bit of attention is the guiding centers here. The guiding centers specify the initial guess for the Wannierization procedure. So by initial guess, I mean the initial guess for this UMN matrix. So it's a parameter to be optimized in this maximally localization routine. So this guiding center provide an initial value for the UMX matrix. The option here, it can be the occupied atomic orbitals in your system. You can infer them from the chemical bonding. Like for water, we know that the localized atomic orbitals, hydrogen-like atomic orbitals is sp3 orbitals of the oxygen atom. So for more details on this option, please refer to the user guides of Wannier90, where you can also find an automatic option for the guiding centers. Now we will have the breakout rooms for 30 minutes. If you cannot finish this exercise in 30 minutes, don't worry. The rest of the exercise does not need the results from this exercise, because I've already prepared a full data set for training the deep dipole model.
Pinchen, we have a question on the chat from Kunapuli Swarup that says, if Wannier center is number of electrons divided by 2, does it mean we're only working in ground state systems?
Yeah. At the current stage, yes. Okay, great. I hope you've also the Wannier centers on our video. Then let's get to the training part. Okay. After doing the Wannier90 calculations, you got the XYZ coordinates of the Wannier centers, right? Then you need to convert the outputs to the training label for the deep dipole. Up to this point, there are no official tools for that. So the workaround is writing your own code to convert the results. You can use ASE to build a neighborhood list for the atom plus Wannier center system, then get the dipole vector for the type of atom you choose to carry the dipole. Like for water, it's the oxygen that you can choose to carry the dipole. After that, you can dump the dipole vector into the raw data file. The structure of the deep dipole dataset is similar to the ones you need for deep potential. I highlighted the raw files you actually need for training the deep dipole. There are 5 essential items: atomic dipole.row, and the box coordinates type map and the type.row. Only the atomic dipole is specifically required by deep dipole model. All other files are just the same ones required by the training of deep potential. So what you need to do is to generate an atomic dipole.row file containing the dipole information. The number of rows of the atomic row dipole is just the number of atomic configurations in this data set. Then the number of columns is the number of atoms carrying the dipole times 3. For example, for this water system, there are 3 water molecules. So you can choose the 3 oxygens to carry the dipole vector. Then the data file should contain 3 times 3 equals 9 columns. In addition to the atomic dipole.row file, you're also allowed to provide a global dipole label. It contains the same number of rows, but only 3 columns, because it represents the sum of the atomic dipole. But this file is only optional. And let's go to the training script. Let's see how the training script for deep dipole is written compared to the input for the deep potential. They are basically the same thing. There's only 2 minor differences. The first one is in the fitting net section. You need to specify the type to be dipole here, and choose the type of atom carrying the dipole. Here, the setup are copied from the training script of water. So the atom type 0 here is the oxygen. For more complicated system containing multiple atom types, you can specify more than 1 type of atom to carry the dipole. You just need to provide the compatible number of training labels in the dataset. The second difference in training script compared to deep potential is in the loss section. Instead of specifying the prefactors for energy, force, and virial, you only need to specify the prefactor for the atomic dipole data and the global data. If the optional global dipole data is not provided, you can make the pref option to be 0. Next, we are going to do 2 exercises in the breakout rooms. The first one is training a deep dipole with provided dataset in this folder. If you still have the training script from yesterday's tutorial, you can compare the provided training script in this folder to yesterday's training script, and you will see the difference. We will have about like 10 minutes for you to set up the training. Of course, for the 10 minutes, it's impossible to finish the training, so please cancel the job if you see it runs successfully and start to give you the outputs. Okay, then after that exercise, we'll do another exercise on the application of deep dipole models. We will see how to use the deep dipole to do post-processing for the trajectory you get from an MD calculation. This way, you can already compute many physical quantities, such as dipole distribution, polarization, dielectric response, and etc. Other than this, more advanced application of deep dipole includes enhanced sampling and accurate electric field-driven MD. But we are not going to cover this part today. For the time remaining, you will only do an exercise on post-processing the MD trajectory. The post-processing exercise needs you to run a molecular dynamics first with only the deep potential model. Then you can execute the Python code I put there for visualizing the dipole distribution of the water trajectory you generated with DPMD. Okay, good luck. Let's get back to the breakout rooms and use the remaining time to finish these two exercises.
How much time do we have for?
All the remaining times, like we have like 30 minutes or so.
Okay, so we have 30 minutes and we will do the following tasks.
Yeah. This exercise will be very quick.
Okay.
Ping-Chen, there's an interesting question on the chat. Perhaps you can answer that. Should I read it to you or would you like to read it yourself?
Let me see.
Maybe you can answer that before going to the breakout rooms.
Okay, I need to, oh, here it is. The question is, do we attribute the dipole of the whole molecule to a single atom in the molecule, or can we attribute the total dipole to more than one atoms in bag molecules where polarizability tensors are localized in space? Yes, you have the freedom to choose what atoms to carry the dipole. Like if a large system has like 10 types of atoms, you can choose the 3 out of them to carry the dipole. You only need to provide the correct data set for that purpose. Okay, we have many freedoms to like divide the total dipole of a molecule to like several parts and attribute it to different type of atoms. I hope this answers your question.
Can you hear me?
Yeah.
Yeah, I was the one who asked the question. Yeah. So yes, we can divide it, but is there any heuristic behind how we divide those dipoles? Do you know?
I think like it depends on how the electrons are localized. Like in water, you know, the electrons are localized around the oxygen atom, right? It's like 4 sp3 orbitals around the oxygen. So for more complicated molecules, you need to like find out how the electrons are distributed, then decide what's the best combination of atoms to carry the dipole.
Thanks.